Well, welcome to another installment of how to use Snell's law to solve a refraction problem. This one's a little different than the other one that I did. The other one, if you've seen it, shows you how to use Snell's law to calculate an index of refraction for some material. This one I've made to show you how to find an angle involved in a refraction problem. The equation is the same, but the solving of it can be a little more troublesome, which is why I made this one separately. Here's a diagram that looks a lot like the other one, except that some different values are given. We still see that a light ray is approaching some boundary between medium 1 and medium 2. This time what I've done, I've specified that medium 1, the white material on top, is crown glass, and medium 2 is diamond. And you could make up any different media that you'd like to. And I've also given the angle of the light ray in the diamond. It's denoted here with the symbol R because that is the refracted ray after reaching the boundary. So what we're going to do in this one is we're going to solve for the angle inside the crown glass. So I'm going to indicate that here with the Greek letter theta, and then I'm going to put a subscript G for glass. I always use subscripts that actually are specific to the problem. They show, for example, the difference between the glass and the diamond. So we're going to start with Snell's law, and I'm going to write it in the form that's most useful and kind of most generic, but also specific to this problem here. What that says is that the index of refraction for the crown glass, so I'll denote that with a little g, times the sine of the angle that the ray makes inside that glass, that's that theta g I just marked, has to be equal to the same quantity on the other medium. So this would be the index of refraction of diamond times the sine of the angle that that ray makes inside the diamond. And notice that we have, as with all problems, 3 out of the 4 values that are given. And we need to find the unknown value, which is the angle inside the glass. So that's our unknown. And you can kind of see that that angle there is wrapped up with a function known as the sine function. Depending on your level of math experience, you may or may not have worked a lot with sines and other trig functions, but I'm just going to show you how to use your calculator to get at that angle. So the first thing I'm going to do is a little bit of algebra. I'm just going to divide both sides by the index of glass, and that leaves me with just the sine of that angle on the left side, and then I get a fractional quantity over here, the index in diamond times the sine of the angle in the diamond divided by the index of the glass. And I think I'm going to actually substitute the values in now. Just don't forget to write the sine function, because what people do is they'll just drop that sine function off. It's like a square root. You can't just get rid of a square root. Now, the index values, as he shows in a lot of his examples, you're going to have to look that up on the table of indexes that's included in the tutorial. On his problems, they have a link back to it. So I would suggest just keeping a tab open with that on there. And when you go back and find that, you'll see crown glass has an index of 1.52 and diamond 2.417. So here we need the diamond first. You see why I'm using subscripts, because if I just put n there, you might be confused as to which n goes where. And then we write the sine of the angle inside the diamond. On his example, he calls that the angle of refraction. I just like to call it the angle inside that particular material. And then 1.52 is the index of the crown glass. Alright, now at this point, you can grab your calculator and punch that in just as it's written here. You would have to close the parenthesis after the 30 degrees. I'll go ahead and maybe put parentheses there just because it'll look that way on your calculator. And you have to make sure that your calculator is in degree mode and not in radian mode. Okay, now the number that calculator is going to give you is not your answer, is the sine of the angle. So you'll see on your calculator, and I might suggest that you actually punch this in just to see that yours is looking like mine. It's 0.795. Now, one of the most common mistakes students make here, if they're not familiar with what a sine of an angle means, is they just think that's the answer, and they'll say like 0.795 degrees, or they'll say maybe 79.5 degrees. But that is not the angle, that's just the sine of the angle. So, to figure out what the angle is, we need to ask the calculator to help us find an angle whose sine is 0.795. And on your calculator, all the TI ones anyway, you'll see right above the sine button, you'll have what's called an inverse sine button. Looks like sine to the -1 power. And so you are going to use that function, the inverse sine of 0.795. You can, of course, keep the extra digits that your calculator gives you. And then your calculator will show you a number that actually makes a whole lot more sense. When rounding here, I'll just take it to 52.7. That is the angle that we're looking for. Now, I always suggest, as does Mr. Henderson on the Physics Classroom website examples, that you check to make sure that your answer is reasonable given what you know about the refraction of light. In this case, we are going from a material that is less dense to a material that is more dense. That's going to cause the light wave to slow down as it enters, and that always causes a bending towards the normal, which means back in the crown glass we have to have a bigger angle than we had in the diamond. And of course 52.7 is a bigger angle than 30 degrees. So in this case we're going from a fast to slow medium. We bend towards. We could do this exact same problem turning those arrows around. So if we have the angle inside the diamond 30 degrees but going towards medium 1, it would refract out into the crown glass at an angle of 52.7. Let me just show you what that would look like in green here. If we have this angle, again that could be 30 degrees, we get the same angle out there. So in this case, if you imagine solving that problem, the Snell's law equation doesn't look any different at all. Okay, so there's this sort of reversibility that we found with mirrors that also works with refraction from different media. So hopefully that's enough of an example to help you feel confident in your basic Snell's law equations. You might look at his other examples as to if you have problems involving triangular shaped blocks of materials and things like that. There's just a little more geometry involved in those. It's not any different physics. And of course, if you have any troubles, you come and see me in the classroom.